for me to welcome our next speaker. So it's Steve Melczer from the University of Waterloo, and as we all know, he is a specialist on analytic combinatorics in several variables. Actually, the title of his talk unites all this. So he will speak on lattice paths as a gateway to analytic combinatorics in several variables. So please start.
Yes, thank you, Michelle. Thank you to everyone for organizing this great conference and attending. So indeed, this is maybe a companion to the talk that Robin gave yesterday, but whereas Robin sort of gave a very high-level view of the theory, I want to be a little more grounded and focused on how this connects to lattice paths and sort of how you can actually use these tools explicitly in your computations. And this will actually tie into a lot of the talks previously given here, for instance, Aline's talk earlier, Mireille's talk, and many of the other ones that we've seen throughout the week. So before I start talking about multivariate functions, I want to start back just by introducing these walks we're looking at and looking at some univariate properties of generating functions, which will have been familiar, which will be familiar to you if you've gone to the talks earlier this week. So of course, this is a lattice path conference. I don't have to explain to anyone here why lattice paths are interesting, but lattice paths are interesting for a variety of reasons. So they're interesting combinatorial objects by themselves. They're flexible enough to encode other combinatorial classes that, as we've seen from the great talks today and on earlier days of this conference, they appear in a variety of applications. And something that was really impressed upon me back when I was an undergraduate student starting to study this under people like Mireille and Aline and Manuel Cowers and Marnie Mishna, is that they also form a very nice playground for experimentation and the development of new tools. And so that's kind of what I want to talk about today. In particular, I want to focus on walks in a quadrant, which again, we've seen multiple times during this week, but just so everyone is on the same page, I'm going to take a set of steps, which will have short steps, so every coordinate will be plus, minus 1, or 0. And I want walks that start at the origin and stay in the first quadrant. And these have been studied, very well studied now. Here's a list of some of the authors that have looked at this problem, and of course, there have been others, many of them at this conference. And one interesting thing is that if you restrict walks, say, to a half space, then it's been known for a long time due to work of people like Ira and Mireille that you'll always get an algebraic generating function. And if you're interested, say, in asymptotics of the walks, then there's a great paper by Cyril and Philippe Flageolet where they tell you exactly how you can find asymptotics. So half space walks are somehow not so interesting anymore because we know exactly how to study them. But for walks in a quadrant, you get this wide variety of behavior. And so you get, you can get rational generating functions, algebraic, d-finite, d-algebraic, or even generating functions that are not d-algebraic. And I'm sure Michael will tell us all about the interesting tools for studying these in his talk right after this. Now, in Robin's talk yesterday, he focused on a connection between algebraic generating functions and this multivariate theory. So here I want to focus more on d-finite functions and how we can connect this to the multivariate theory. And so just to remind everyone, if I have a generating function, say the generating function of walks, then I'll call it d-finite if it satisfies a linear differential equation with polynomial coefficients. And this happens if and only if the coefficient sequence is p recursive, which means that it satisfies a linear recurrence with polynomial coefficients. And something to note is that if I have an algebraic generating function, it's encoded by an algebraic equation, and there's a finite number of solutions to this equation. Now, if I have this differential equation, there's going to be an infinite number of solutions, but they form a finite dimensional vector space. So we can still manipulate and encode the solution space with a finite amount of information, which is a basis. And I started looking at this problem. So back when I was an undergraduate at SFU in Vancouver, working with Marnie Mishna, she had me look at these very nice asymptotic conjectures by Aline and Manuel Cowers, which I believe Aline mentioned in his talk earlier this morning. So they took all these interesting walks in the quadrant. They computationally generated many terms. They tried to guess d-finite equations that they satisfied. And then for the ones that did satisfy these linear differential equations, they tried to guess asymptotics. In particular, the constants, if I remember correctly, for most of the constants, what they did is they numerically calculated the constants to high accuracy, and they tried to by generating, say, the 1000th term of the sequence, and then they tried to recover what the constant should be by guessing the constant. So the constants were the hardest part to recover. And if you want to be a little more rigorous, there's this very nice sort of framework you can follow now, which is to introduce a multivariate generating function tracking not only the length of a walk, but also its ending point. So here it would be a 3-variable generating function because you're keeping track of the x endpoint, the y endpoint, and the number of steps in your walk. You can derive a functional equation for this trivariate generating function, and then you can use the kernel method developed by Mireille and others to write this generating function that you started with as the so-called diagonal of a rational function, which I will describe in much more detail later in this talk, and Robin also described yesterday. And so, there's this great paper by Mireille and Marnie Mishna where they do this very systematically for these walks in a quadrant, and they classify sort of when you get these definite generating functions. Now, if you have this rational diagonal, as Aline described in his talk this morning, you can compute an annihilating differential equation using tools from computer algebra, so it's creative telescoping methods. And so this is sort of a follow-up paper to the original paper of Aline and Manuel, where they conjectured asymptotics, where they proved the differential equations, and they also tried to solve them in terms of hypergeometric functions. And I believe, as Aline discussed in his talk this morning, then they were able to get some asymptotic information from that as well, but there were certain models that could not recover the asymptotics of. So when you have these differential equations and you can try to find asymptotics, you can try and do specialized methods like solving in terms of hypergeometric functions, or you can do other methods, which I'll show shortly, but the hardest part is always getting this constant. So let's look at an explicit example. So let's take north, south, east, west walks in the first quadrant. And if you run this methodology, you'll get that the generating function here satisfies this differential equation. And from here, you can automatically calculate a recurrence for the number of walks, which is this recurrence right here of order 2. And so the solution space of this is a vector space of order 2. And there are methods that allow you to compute a basis of solutions whose expansions at infinity, essentially, you can compute terms in. So there's a very nice paper by Doron and Jet Wimp where they describe how you can find these expansions, but the idea, all you need to know now is that it's automatic. So you can take this recurrence, go into Sage or Maple, and it'll tell you there's a basis of solutions. So here we have 2 solutions, and you can compute an arbitrary number of terms and their asymptotic expansions. Now, we have a particular sequence that satisfies this recurrence that we're interested in, the counting sequence. And since this is a basis of the solution space, it means we can write the sequence we're actually interested in, the number of walks, as a linear combination. So there are constants C1 and C2, so that our sequence is this linear combination. And now the real question is, how can we compute these coefficients C1 and C2? So of course, we can estimate them. For instance, you can compute the number of walks of length 1,000, and then divide by 4 to the 1,000 and multiply by 1,000, and you'd get an approximation for this C1. But can we do something more intelligent? Can we do something more rigorous? And eventually, can we determine these constants exactly? And to do that, what we're going to do is we're going to go back to the generating function. So of course, as many people in this community will be familiar with, there's a strong link between the analytic behavior of your generating function and the asymptotic behavior of the sequences. So in particular, in this case, your generating function will have singularities at 1/4 and -1/4. And if you take an expansion near these points in a suitable region, then near 1/4, you'll have a series expansion whose first term, so the most impactful term, is basically this constant C1, so the constant that appears here, times a logarithm plus something else. And near z is equal to -1/4, then you'll get another expansion whose leading constant here is this C2 divided by 2. So if we can recover these expansions of our generating function, then we can recover these coefficients and we can say strong statements about the asymptotic behavior. So now we're going to go back to the generating function. We're not going to look at the recurrence anymore. And again, the solution space to this linear differential equation is a vector space. And so there are very classical methods, going back at least to Frobenius, that allow you to compute series expansions. I should say that in general, the solutions to a definite equation can be quite nasty, but in the examples that I'm going to be looking at, we get sort of so-called regular singular points, which are a bit nicer. And so using this method of Frobenius or similar methods, we can again compute a basis of solutions and expansions to this basis for any point in the complex plane. So for instance, we could say I want a basis of solutions whose expansions at the origin I know, and there are methods to compute this. So here, here we have there's the third derivative here, so we have a basis of 3 elements, and this is a solution. And so our generating function, again, it's a solution to the differential equation, and since we have a basis, it will be a linear combination of the basis elements. And how can we figure out what the linear combination is? Well, first of all, there's a logarithm in the first term here. So this coefficient must be a 0 because our generating function, when you expand it to the origin, it's a power series. It doesn't have any logarithm. And then here you're dividing by a z. And again, we have a power series. So this coefficient must be 0. And then, looking at the initial terms of what we compute here, then the initial constant, say, is a 1, and our generating function has a 1 and as a constant, so there must be a 1 here. So I'm writing here what was returned to me by Sage. Of course, a basis, you could multiply any of these by constants and you get another basis. The basis is not unique, but this is what's returned by this nice Sage package, which I'll show more of in a second. And so that's at the origin, but what I really want is information about my generating function near these singularities, so near 1/4 and near negative 1/4. So I can, again, try and apply this method near z is equal to 1/4. And again, I would compute a basis of solutions. It might be a little small now. I hope everyone can see this. If you can't, the main point is that we get two power series here. So two functions which are analytic at 1/4. And one up here that has a logarithm singularity. And again, we can write our generating function as a linear combination of this basis elements. And this time, to find these coefficients, it's a bit trickier because when we expanded near the origin, we can compute the power series expansion of our generating function at the origin because these are just terms of our sequence that we're interested in. So we know a lot, as much information as we want about our generating function near the origin, but we don't know very much about it near z is equal to 1/4. So it's not obvious how to compute these coefficients, at least at the beginning. But you'll notice that, again, we have this logarithm here. And so if we match up what we had before, we wanted to find this coefficient, C1, which appeared in the asymptotic expansion. And this is just basically this coefficient here, except really I had a log 1 over something before, so there's a negative sign coming from properly manipulating the logarithm. But essentially, if we can compute this expansion of our generating function, if we can compute these coefficients here, then we can give the dominant asymptotic behavior of our sequence. So now what we've reduced to is finding these coefficients. These are sometimes called connection coefficients or connection constants. And so here's just a little preview of how you can do this in Sage. So I'm using the Ore algebra package, which was originally developed by Manuel Cowers and his collaborators. And it's been worked on quite a bit in recent times by Mark Mezaroba, who has implemented some of the things I'll describe for computing these connection coefficients. And so you import the package, you define the rings that you're working over. Actually, I don't even need this first line here. This is developing recurrences. I'm only using the differential part here. I enter the differential equation, and I ask for a local basis. So there's this command, local basis expansions at 1/4, and it tells me there's these 3 elements with a log. The first one has the logarithm in it, and there's 2 power series. And it computes initial terms, but it also tells you if you have logarithms, you'll have at most a finite number of logarithm powers, and it tells you how many you expect and things like this. And yeah, so now we're just back to this question: how do we compute these coefficients here? So I don't want to go too much into this, but there is a very beautiful sort of combination of theory and computer algebra that allows you to approximate these coefficients to arbitrary accuracy. And its basis lies in very classical methods. So, I have my solution at the origin that I know a lot of information about. I pick some other point, let's say arbitrarily close to the origin. So this might not be 1/4, it might be closer to the origin than 1/4. So let's just suppose we have something sufficiently close. Then there's this method of majorance that goes back to Cauchy that allows you to bound. So if you take the power series expansion up to the nth term, you can find an explicit upper bound involving a constant and some power which is between 0 and 1 raised to the power of n. And so it allows you to approximate your function to some arbitrary accuracy by taking initial terms of the sequence. And so basically you say, say I want 100 decimal places, well, you can say that to get 100 decimal places, I would have to, I can approximate my generating function by the first 100 terms in its power series expansion. And then, you can approximate the coefficients to a certain accuracy. So you can decide accuracies for all these things, and then you can approximate your generating function at this point, say A over here. And of course, you can not only approximate your generating function, but you could approximate its derivative and second derivative, because these are also d-finite functions. And then that allows you to recover an expansion of your generating function at this point A, it's arbitrarily close to the origin, where these coefficients are approximated up to arbitrary precision. So you give a precision, and you can approximate them to that precision. And again, I don't want to spend too much time on this here. It's not really the focus of this talk. But if you want to learn more, so there's a nice paper by Joris van der Hoeven from 2001. But really, Mark Mezeroba is kind of the master at this. So he's been looking at this problem extensively since at least his PhD thesis back in 2011. And he's developed beautiful code in Sage for not only implementing this, but implementing it extremely efficiently. So you can learn the theory if you want to, but honestly, you don't really even need to, because Mark has done such a great job implementing this that you can apply it and get really powerful results just from using his code. So this was for approximating, from the origin to a point near the origin, but of course you can chain these approximations together, and you're doing essentially an infinite continuation with rigorous numerics. And again, it's a really beautiful combination of the theory and some very advanced computational methods. I'm skipping over a lot of the computational methods you need to do in order to get this to be extremely efficient. So on our example, here's just a quick look at what happens in the code. So there's this command numerical transition matrix. This tells you if I have a basis at the origin and I have a basis near z is equal to 1/4, how can I write one basis element in terms of another basis element? So it's converting between these bases. And so you see here there's this matrix with numbers in it, and it says plus or minus some values. So these are approximated numbers with rigorous error bounds. And here I asked for 1 decimal place. But again, as I said, this code is very efficient. So in under a second, you could for sure get hundreds of decimal places, maybe even thousands of decimal places in this example. So you can really go very, very quickly. And so in this case, again, I'm skipping over a few of the details here, but the upshot is we can compute this expansion of our generating function near z is equal to 1/4 with coefficients that are numeric and approximated to arbitrary accuracy. So in particular, we get this asymptotic expansion. So we compute the C1 coefficient, which is 1.27 something something something, and here I have it up to 17 decimal places, but again, I could get it up to 100 decimal places in under a second if I wanted. So this is great for approximating these constants, but you might ask, what are these constants? Something a little more pathological can happen as well. So let's look at a slightly different example. Instead of north, south, east, west, let's look at these, I think they're called trident walks, or maybe they're negative or called trident walks. I can never remember all the funny names people come up with for these things. But we have this set of steps, again, in the quarter plane. So now you have a linear recurrence of order 6 that the counting sequence satisfies. So that recurrence has 3 solutions whose expansions look like this. So a 3 to the n, and then 2 terms which are slightly less than 3 to the n, and then everything else is asymptotically lower. So it doesn't really matter. And again, we can write some linear combination. Our sequence will be some linear combination of these. But now if you do this numeric method, you'd calculate that C1 is 0.00000, with many zeros, and then C2 and C3 are something non-zero. So you might think that you're growing like 3 to the n, but numerically it seems like actually this is going away, and you're going to grow like 2 root 2 to the n. And so again, it's, if you can compute this constant to 1,000 decimal places and they're all 0, it's pretty good evidence that it's actually equal to 0. But we'd like to be able to decide this exactly. It's actually still an open problem in general if we can decide when these coefficients are exactly equal to 0. And so the problem really is that we need bounds on these constants. So if we had bounds, we could compute to whatever accuracy we need to decide that, yes, it's exactly 0, or no, it's not 0. Of course, if the constants are non-zero, we can eventually decide that just by computing to enough accuracy. But we don't know in general if we can prove equality to 0. The other thing is that in order to get the differential equation, we go through this diagonal representation. So can we start with the diagonal representation and get asymptotics directly from there? And then, maybe if we don't have to go through the differential equation, we can do things like add parameters, which is harder to track when we do these computer algebra or these creative telescoping computations to get down to the differential equation. So in order to give, to prove, for instance, in this case, that you have exactly 0, and more generally to give explicit representations for these constants, we need another representation. And so this is why I originally started looking at this multivariate asymptotics technology, was to try and prove these asymptotics of Aline and Manuel, and more generally to look at different lattice path examples. And then, this multivariate stuff that Robin and Mark had been doing back then, and Yuri Brezhnikov, was so beautiful that then I started looking more and more into the theory behind all of this. So that's the background for why we're interested in maybe looking at these multivariate asymptotics. Now I'm going to take a little bit of step back and start explaining, again, what the multivariate asymptotics are all about, and then I'll connect it to lattice paths in a little while. So now we have a multivariate series in d variables, and I use multi-index notation. So everything that's bold would be you can think of this as a vector, and a bold z to a bold I is a product, z1 to the I1 up to zd to the id. And eventually I'm going to be interested in a univariate sequence. So the most common way to do that is to look at what are called the diagonal sequences. So essentially you pick a vector r, and you look at all the terms whose indices are multiples of r. So for instance, the main diagonal, if you set r equal to all ones, these are the terms where all the exponents are equal. So if I take this rational function here and I expand it out, I get the constant, the coefficient of x to the 1, y to the 1, the coefficient of x squared, y squared, and so on and so on. If I looked at the 2, 1 diagonal, then again I'd have the constant. Now I have x squared, y to the 1, x to the 4, y to the 2, and so on and so on. And there's this nice nesting of structures. So again, I believe Aline touched on this in his talk this morning, but the class of diagonals, it fits between algebraic functions. So 2 variable diagonals are equivalent to the class of algebraic functions, and it sits inside d-finite functions, and it's not really understood exactly how they fit in each other. So in Aline's talk, I believe he talked about this conjecture of crystal, which says that if you have a function that's d-finite, and for instance has integer power series coefficients which grow at most exponentially, then your function can be expressed as a multivariate rational diagonal. I think Robin also mentioned this in his talk. And in fact, there's explicit examples. So his general conjecture is slightly stronger than what I wrote here, but Crystal gave this example back in 1987, and as far as I know, no one has been able to express it or prove that it can't be expressed as a multivariate rational diagonal, even though it is a d-finite function. And it satisfies the slightly more general form of Crystal's conjecture. And if you're interested in learning more about this, I would recommend that you ask Aline, because he's kind of the expert, one of the experts on this right now. In particular, he has this recent work which looks at these kinds of questions that was posted on the archive a few months ago. Oh, some of my some of my things are not appearing. Ask Aline Bostin. Sorry. So, right here. Yeah. Okay, so now it's appearing that some of my math is not appearing on the slides. Hopefully this is just for this slide. So everything else appears to be working except for what was written right there. Okay, so we have this multivariate function. Now I'm going to assume for this talk that we have a multivariate rational function. So I can write it as a quotient, g over h, where g and h are coprime polynomials. So more generally, you can deal with meromorphic functions. And there's a little bit of work for algebraic functions, although as Robin said in his talk, usually to deal with this, we would try and write it as a diagonal of a rational function in a higher number of variables. Now, the singularities of this generating function, so f of z, it's given by the zeros of the denominator. And I'll write this as a script v. Now, the singularities that excuse me, the singularities that are closest to the origin, these are called minimal points. So for those who have seen the univariate theory, these are often called the dominant singularities. The difference now in the multivariate case is that your singular set is going to be an algebraic set of positive dimensions. So you're going to have an infinite number of singularities. You're going to have an infinite number of minimal points. Whereas for univariate functions, you usually have, yes, thank you, Sergey. Yeah, I should also mention that you can download the slides either from, I don't know if you can download them right here on BBB, or there, I put a link, if you scroll up in the chat a little bit on my website, I put a link directly to the PDF on my website if there's anything that's not clear because something is missing on the slides. So as I was saying, the singularities that are closest to the origin, these are the minimal points. And so these are very important, as you might expect, coming from the univariate case, although they're maybe not as important as you might think, and I'll explain more about that in a little while. But our main tool, just like in the univariate case, is going to be the Cauchy integral formula. So the Cauchy integral formula, there's a higher dimensional generalization. So you, instead of 2 pi I in the front, you put a 2 pi I to the d. Again, here I'm sort of taking a product of the variables to the powers that are given by this vector. And instead of integrating over a circle, you integrate over a product of circles. So, you know, the modulus of z1 is equal to some constant, the modulus of z2 is equal to some constant, et cetera, et cetera. And so just like analytic combinatorics finds asymptotics of a univariate sequence from its generating function, ACSV, analytic combinatorics in several variables, does the same thing using complex analysis in several variables and multivariate generating functions. So because we're dealing with these multivariate generating functions, things can get very pathological. So in this talk, I'm just going to restrict to the easiest case, which is usually called the smooth case. And so for us, that's going to mean that your denominator and its partial derivatives don't simultaneously vanish. So for every point that's a 0 of h, one of the partial derivatives of h does not vanish. And this means that your set of singularities forms a manifold, so this is why we call it the smooth case. And there are a set of points which are called critical points. So Robin talked about them extensively in his talk. And for us, in this smooth case, these are just the points that satisfy this set of algebraic equations. So your denominator is 0, and then there's some set of equations that depend on partial derivatives with respect to your variables, and this direction r that you're trying to find asymptotics in. And the nice thing about this is that generically, if you randomly picked a polynomial h, this would be a finite set. So the idea is that you have d polynomials and d variables, so generically you're finite. And there's a little bit more work to fully proving this because, you know, your polynomials are structured, they depend on each other, but you can show that generically, so with probability 1, if you randomly picked an h, you'd get a finite set of critical points. So here I wrote everything in terms of z1, but you could replace z1 with z2 or zk. It doesn't matter because you have the equalities. So it is actually symmetric, even though the way I've written it, it does kind of make z1 seem special. So yeah, so we have these two types of points. And critical points, essentially what happens in the multivariate theory is that you take some kind of residue to go from a d-dimensional integral to a lower dimension. And critical points are the ones where after doing this, you can make an asymptotic approximation using a saddle point method. So critical points are kind of points where you can locally get asymptotic expansions using something like the saddle point method. And minimal points, these are the ones on the boundary of the domain of convergence, or these are the ones that are the singularities that are closest to the origin. These are the ones where you can deform your Cauchy integral to be very close to, because there are no singularities closer to the origin. So when you have minimal critical points, you're in a very good situation, because you can deform to be close to them, and then you can probably compute an asymptotic approximation of them. Now, the asymptotic contribution of a minimal critical point, it depends on an explicit matrix, which is built from the partial derivatives of your h polynomial. And I'm not going to show it. It's quite large, and unseemly, but it's in the slides, in the bonus slides, if you download the slides, or you can look in my book or ask me. The point is that there's some explicit matrix we can build, which will appear in the asymptotic formula. So here's a theorem, and this is a theorem, a fairly general theorem, so it'll allow us to get a lot of asymptotic results. So let's suppose that this system of critical points has a finite number of solutions. And again, generically, if you randomly picked an H, this would be satisfied. Then let's suppose there's exactly one minimal solution, which has non-zero coordinates. So when I write C star, that means you don't allow a coordinate to be 0. Let's suppose the partial derivative with respect to the final variable is non-zero here. And this matrix that I didn't define but is explicitly given has non-zero determinant. Then you have an asymptotic expansion of your rational function, and the leading coefficient here. So in the numerator, we have the numerator of our rational function evaluated at this point. So if this evaluation is non-zero, we've given a dominant asymptotics. Now, if this evaluation is equal to 0, you can compute higher order terms in this expansion. It could also be that actually all the terms in this expansion are equal to 0, and then you have to do a little bit more work to try and figure out another point that would determine asymptotics, but I don't want to go too much into that right now. As Robin said, so if M is not full rank, so if you have so basically what happens is this determinant being non-zero, this means that you'll get a saddle point integral that's non-degenerate. So you can say explicitly what happens. If the determinant is 0, you would get a degenerate saddle point integral. So in one variable, that would be like, instead of integrating e to the negative n x squared, it would be like e to the negative n x to the 4 or x cubed or something like this. So if the determinant is 0, you can still get asymptotic results, but it's a little bit messier because you have to deal with these multivariate degenerate saddle point integrals. But there are still techniques for dealing with it. But for instance, the behavior that I get here, this comes from a non-degenerate saddle point, so which is why I'm assuming that this determinant is non-zero. And as Robin said, if you vary this direction in some compact set where these assumptions are all satisfied, then the error term that appears here, so the constant in this big O, can be uniformly bounded. And this allows for a lot of beautiful results like limit theorems, which I don't have enough time to go into in this talk, but you can get a lot of nice stuff from that. It also means that here I'm stating asymptotics in R diagonals, but of course, I think this was even asked by someone else earlier this week, maybe in Robin's talk. What if you don't look specifically on an R diagonal? What if you go like, n plus square root n comma n? And because of this uniform behavior, this is sort of, it allows you to deal with other situations that are not exactly R diagonals. But again, that's kind of another topic that I don't really want to spend too much time on right now. I would rather sort of give some explicit examples to help people have confidence that they can really apply these methods themselves. So let's look at this very simple example here, this rational function, which has binomial coefficients in its coefficients. So this set of equations is just this set of equations, and of course, if you solve it, you'll get one solution, 1/2, 1/2. Now, the thing that's not automatic here is to prove that this is, in general, is to prove that this is a minimal point. So there's no point that's coordinate-wise closer to the origin. But here you can just check, because we have a very simple polynomial, that if the modulus of x is less than 1/2 and the modulus of y is less than 1/2, you can't get x plus y equal to 1. So it's in this case, it's very simple, so you can easily show that it's a minimal point, and then we can get asymptotics. You can also look in the general RS direction, so the only thing that really changes is that now we had 1, 1 here before, now we have R and S appearing. The minimal critical point will depend on R and S, and again, you can compute this asymptotic expansion. If you look in my book, which I described yesterday in the book, in the session dedicated to new books, I spend about maybe 10 to 15 pages just on this one example, driving everything from scratch to show how all the computations go. So going back to lattice walks, let's look at, say, the north, south, east, west model that we saw before. Now that's very nice, and one of the reasons it's nice is that it's symmetric over every axis. If you flip over the x-axis to the y-axis, your set of steps is invariant. So in general, if we take any set of steps in an orthant, so in n to the d, which is symmetrical over every axis, you can get a uniform rational diagonal expression for your generating function. So it's the main diagonal of this rational function, where this S here, the octoplane is not an orthant. so this set of steps here, S, is the sum of monomials whose exponents are the steps you're allowed to take. And so from this uniform diagonal expression, you can actually verify that the hypotheses of the condition I put before are satisfied. The only thing you can't verify right now is this matrix M, because I didn't give you the formula right now, but if I gave you the formula, you could easily verify it. And so this was with Marnie Mishna, again, back, I think this was during my master's at SFU, we gave this rational diagonal expression, and from that, you can give dominant asymptotics that depends on the number of steps you take. And these small s's here are the number of steps that move forward in the first coordinate, the second coordinate, all the way up to the dth coordinate. So a very explicit expression for dominant asymptotics. And you can also compute, higher terms in this asymptotic expansion. It just gets messier and will depend more on the specifics of the steps that you're looking at. More recently, when I returned to this for writing my book, I gave some refinements. It's not so important, this is a big theorem, but you can do things like parameterize your starting point. So instead of starting at the origin, you can start at a point P. You can count on walks that go back to some of the boundary hyperplanes, so hyperplanes in some set A, and then you can give a refinement for the number of walks that do that. And again, it's quite explicit for the results that you get. Here, what you have to do is you sort of, the higher order terms that appear, there's an explicit formula for them, but it involves taking high powers of some kind of differential operator and applying it to certain functions. So you have to be a little careful about when you're applying these things. In the original work with Marnie, we kind of didn't really want to get into that. But when I was rewriting this, I realized it's actually not so messy. You just have to get your hands a little dirty, and you can get these fairly nice expressions in the end, even though they're a little unwieldy when you first see them. You can do other modifications. So you can, that was for steps that are symmetric over every axis. You could say, what if I'm symmetric over all but one axis, for instance? So it's been known for quite a while. You'll get G-finite generating functions. So there's some work of Mireille on this, maybe some other work that I'm forgetting now. But for instance, if you have walks that are symmetric over all but one axis, let's say we have this step set here, and we add weights. So it's not going to be symmetric if A is not equal to B. And if A is larger than B, you're kind of moving away from your boundary restriction. If B is greater than A, you're moving towards the boundary restriction. And then you can again get asymptotic results. So this is work with Mark Wilson. And for certain situations here, you need a generalization beyond smooth points. So in some cases, these sort of smooth points will determine the asymptotics. But in other cases, you will not look like a smooth point. You'll have singularities, critical points, that will determine asymptotics, where you locally look like the union of hyperplanes. And so in this case, I believe it's if A is bigger than B, then you'll have to do some kind of asymptotic computation where you're not a smooth point. And if B is larger than A, you will get a smooth point. And of course, if B is equal to A, this is just the regular north, south, east, west steps. So after doing this, this covers actually a lot of these asymptotic conjectures of Aline and Manuel. So there are some that have algebraic generating functions, which can be handled by univariate methods. And the other ones, most of them are either symmetric over every axis, like these four, or they're symmetric over all but one axis, like these kind of ones. Then there's a couple sporadic ones you can just finish off by hand, along with the algebraic ones. Again, you can generalize this in other ways. So you can add, you can add more general parameters to your sets of steps. So here's some other work we did where we took a look at this set of steps, the so-called Guy-Bouchon model, with a particular weighting. And if you weight your steps like this, you actually get a rational diagonal expression where the parameters appear in this multivariate rational function. I believe Lin Xiao asked about this yesterday after Robin's talk. What happens if you have, can you put parameters in your rational function? So you can, and as you vary your parameters, then the geometry of the singularities that determine the asymptotics will change, and this will give you sort of these sharp transitions in asymptotic behavior. So your exponential part of your growth will always vary smoothly with your weights, but the sub-exponential part, the sort of polynomial part, you get this exponent, and this will transition between some finite set of values as you go over these different directions. And this was joint work with Julien Courtil, Marnie, and Killian. And in particular, on the boundary regions here, things get sort of nasty, and so we did some explicit residues by hand, and then applied the general theory after to do a little bit of extra simplification there. And again, by now, hopefully I've convinced you that these apply very generally, so you can take more work, like for instance, work that I think Aline and Mireille might have described earlier today and this week, that if you have sets with long steps, you'll get some diagonal expressions in the nicest cases, and then this technology immediately applies. Not only that, but in the nicest situations, this is all very automatic. So with Bruno, during my PhD thesis, we gave sort of algorithms that allow you to verify the conditions of the theorem that I put up before, and then give you an asymptotic expansion if the conditions are satisfied. And so we have algorithms that will allow you to find all minimal critical points, and then compute asymptotics assuming these nice conditions are satisfied. Again, most of the conditions are generic, so randomly, with probability 1, you'd expect them to hold. Of course, in actual combinatorial examples, you get non-generic behavior quite frequently, but still for combinatorial examples, a lot of this does hold. And as Robin said, I think in his talk, we have these two groups now coming out of this math research community workshop we did a couple weeks ago that are trying to give really nice implementations of this in Sage and in Julia. And so these will hopefully be finished quite soon. For now, thank you, Sergey. So there are some bounds here that I'm giving, but it's not so important to understand this slide. The main thing is that we have algorithms and that there are some complexity analysis that goes along with that. Exactly what happens is not so important for this talk. So if you're interested in applying this completely automatically, there is some code that goes along with my textbook. Bruno and I also wrote a Maple package which implements some of this. But if you wait a little longer, then we're going to have this. Hopefully, I think it's going to be a very nice package in Sage that you can use. So just at the end of my talk here, I want to say a little bit more about the general theory and connect this back to this connection problem, so definite asymptotics that I mentioned at the beginning. So in the univariate case, the singularities that are closest to the origin dictate your dominant asymptotic behavior, right? The dominant singularities. So you might think that the minimal points will be the ones that give you asymptotics in the multivariate case. But in fact, that's not true. So basically, because you can't generalize from one variable is too restricted to really see what happens when you go to more variables. And so it turns out that the critical points are the ones that actually matter more, not the minimal points. Essentially because when you're dealing in even two variables, that's four-dimensional real space. So it's hard to visualize, but you have enough dimensions that you can basically manipulate, or you can maneuver your domains of integration around the minimal singularities. So it's very hard to visualize these things. I think it's one of the biggest barriers to making the multivariate theory understandable is that you can't even in two dimensions get a truly accurate picture. But minimal points don't actually come up, or they're not as important as you might think. It's really the critical points that matter. Now, here I talked about the smooth case. What happens in the non-smooth case is that you partition your set of singularities into smooth sets with certain conditions, and then you calculate the critical points on each of these smooth sets that make up your singular variety. And so when there are these minimal critical points, then usually some of them will be the ones that determine asymptotics. Again, you can always cook up pathological things where this is not true, but in practice, most of the time, if you have minimal critical points, you're in a pretty good situation. So when you have these minimal critical points, so a minimal point, just to remind you of the definition, these are the ones that are on the boundary of the domain of convergence, or these are the ones that are closest to the origin. So coordinate-wise, there's nothing closer. There's nothing with smaller coordinate-wise modulus than this singularity. Okay. So when there are no minimal critical points, or you have minimal critical points but they don't contribute, then it's harder to know what to do. And so again, the reason, I think someone was asking, maybe it was Sergey was asking about this before, was how do we do our domains, or how do we deform our domains of integration when we're doing this? So if you have a minimal point, because it's on the boundary of the domain of convergence, or because it's coordinate-wise closest to the origin, you can actually deform close to it just by doing, by deforming your the moduli of your coordinates. So you can basically take the circles you're integrating over and expand the circles to get close there. So you don't have to think too much when you're trying to do these deformations. But if you have to go beyond minimal points, then this is quite difficult, because it means that locally, on some parts of the domain of integration, you can keep pushing outwards. but maybe near the minimal point, you have to be a little bit more careful. So you can't just do such a brute force deformation by just increasing the modulus of each coordinate. You have to actually take the local topology of the set of singularities into account. And so this is why we've started bringing in this Morse theory approach, because we need to sort of get our hands dirty and understand more about the local structure of the set of singularities to know how we can actually do these deformations. So this is why we started using all this Morse theory technology, or I guess, well, really Robin, Mark, and Yuli started using this before I came around, so I don't want to speak for them for why they started using it, but in my mind, this is why the Morse theory is so useful and why it gives us such nice results, is because it allows us to understand the topology and how we can make the deformations that we need beyond the simple case of having minimal critical points. So the largest difficulty will be how do we deform our domain of integration? And so what Morse theory describes is it tells you something about the topology of spaces using functions from that space to the real numbers. So here, let's say we're looking at the main diagonal, we have this rational function here. And so the part of this integrand that is sort of captured by n, as we're taking n to infinity, is the denominator here. So the modulus of this is sort of approximated by 1 over the product of the moduli. And if you're looking in more general directions, you'd replace basically the 1 in all these exponents by something that depends on the direction you're looking at. And when we're integrating, if we start by integrating over products of circles near the origin, essentially you're going to have a curve of integration that has very high height, because if everything is close to 0, this is going to be really large. And again, when we're expanding our circles of integration, you're sort of bringing the height down. So we want to take this cycle of integration and push it to lower height. And so you can do this, and we don't want to cross our singular set, so this right here is our singular set. And I should thank Robin, because these are his pictures that I stole and I'm using for this talk. And you can keep pushing downwards until eventually you get stuck. And it turns out that when you get stuck here, you're going to have a critical point. And so again, you can kind of take some residue maybe, and eventually you're going to end up with something that looks like a saddle point integral, and that's not so surprising from this picture that you get something that looks like a saddle point integral. But the problem, as Robin talked about more in his talk, is that this height map on a variety, it's usually not proper. I mean, generically, it's not proper in 3 dimensions or greater. So the problem is that you can deform downwards, you can keep deforming downwards, but stay at bounded height, because you could have sort of an asymptote that looks like this. And this asymptote here, this is what Robin was talking about when he talks about critical point at infinity. It's something that sort of you get stuck on, but you don't get stuck on it because it's really a saddle point. It's because you sort of have this asymptote that goes out and stays at finite height. And so this is really something that was a sticking point in the ACSV theory for a long time, and why the Morse theory was not used for rigorous results originally. It was used to motivate, if you look in Robin and Mark's, the first edition of their book, it's used to motivate a lot of their constructions, but it's never used to prove anything, because back then there was no way to rule out this happening. But as Robin mentioned in his talk, we now have these checkable conditions. So there's an algorithm using Grosvenor basis computations, which has been implemented in Maple, and we're hoping to improve it using things like toric varieties and sort of a different approach. So there are these checkable algebraic conditions under which the results of Morse theory hold, and so we can write our sequence of our diagonal that we're interested in as a combination, essentially, of saddle point integrals, a linear combination of saddle point integrals, plus something which is asymptotically negligible. And again, there's some very pathological things where this wouldn't hold, but essentially this is true. And the idea is that we need to, again, compute these integers. So I think I'm just at the end of my talk, so I'll just spend 2 minutes describing how we get these integers. And this connects back to what we already saw for d-finite functions. Because if you have a rational diagonal, it's going to be a d-finite function. So we have this technique for approximating these connection coefficients. And now we have a way of writing asymptotics up to an integer linear combination of things that we know the asymptotic expansions before. So we can try and combine these. And this goes back to what Andrea was saying yesterday, I believe. So let's look just at this example, which Robin also mentioned in his talk. There are 3 critical points, it turns out. one that looks like 81 to the n and two other ones that have other behavior. And you can check that there's no critical points at infinity, so we know we have a linear combination of these sort of asymptotic expansions. Really, this is the beginning of an asymptotic expansion, so this should be plus dot dot dot, this should be plus dot dot dot. If you compute the differential equation and then get a recurrence, you'll get a vector space of solutions. And so again, you can say that you're going to be a linear combination of these two, where now these sigmas are just complex numbers instead of integers like they were on the previous slide. But the idea is that we can use this numeric analytic continuation from the first part of the talk to approximate these rigorously. So we have two representations, one with unknown integers, the other with approximated complex numbers. And when we combine them, we can exactly say what they are. And so in this case, if you do that, you'd get that this K1 is equal to 0 and exactly 0. K2 and K3 are 2.999. You can get them to 1,000 decimal places in a couple seconds, but you only really need one decimal place to know that it's exactly equal to 3. And then you get this asymptotic result, which Robin mentioned. It's actually slightly nicer because this tells us something about the global, or about the topology of the set of singularities. And so we can actually say, as you vary in directions, what happens asymptotically as well. Now, just to wrap up, so the kernel method and analytic combinatorics and several variables are a very potent combination. We have 7+ years of results at this point, and anytime someone comes up with a new thing using the kernel method, it's not so hard to just slip in get some asymptotics using these techniques. The reason that it's nice is that these diagonals, they form another useful data structure, right? It's not always understood if you have something just from the differential equation how to get a rational diagonal representation. We don't understand this. But oftentimes, like when in lattice path enumeration, we actually go through the rational diagonal to get a definite equation. So if you have the rational diagonal, you can often get asymptotics directly from this, and you can work around this connection problem things. The results of ACSV are very powerful, and in many cases, they reduce to conditions that can be checked algorithmically, and we're even having code for this now. And ACSV, it's rapidly expanding. There's many directions to expand in, and in particular, I'll say that the directions that we expand in, they're heavily influenced by cool applications. So if you have some cool applications, you have some multivariate generating functions that you're interested in analyzing, it'll really motivate us to expand in the direction that you need if you tell us, because then if we have cool application, we'll want to look at that more. So thank you very much for your attention. If you want more information, as I mentioned yesterday, I have a new textbook out about this, and it goes through all the examples that I talked about in this talk in much more detail. Thank you.
So thank you very much. So questions?
Yes, I have a question. This is fascinating how powerful you can get. So the Morse theory is implemented yet? Can you teach a computer how to do the Morse theory?
So this is something I would like to do to simulate these flows and things like that. But right now we don't actually need to, because you can just basically compute the terms that it's an integer linear combination of, and compute with the d-finite function, and that they have to match up, because that you'll get the integers. So I mean, the power of the Morse theory is it tells you what will happen if you flow. It's not that you actually have to do the flow, right? It tells us what would happen. So I do actually want to implement something that simulates the flows to help visualize it and get some interesting information, but we don't actually need that. So most of what I talked about now, you can do with existing code already. Yeah.
Thank you. Another quick question / suggestion. This is such a powerful technique. There's a bunch of some of them still open productivity conjecture by diagonals about productivity of rational functions. Some of them goes back to Askin and Gaspar, and Alan Sokal had a beautiful proof for one case, and Manuel Carlos and I considered some cases, but some of them are still open. So yes. Can you use asymptotics and maybe possibly to prove positivity by finding that eventually it will be positive and then check numerically the first cases?
Yeah, so two things to say about that. First is this example comes from your paper, one of your papers on these positivity conjectures. The second is I have some separate work with Mark Mezaroba and right now a master's student, soon to be a PhD student, Ruan Dong, about finding definite asymptotics with explicit error bounds. So you can do exactly what you said, where you can say that asymptotically when n is greater than 1,000, it will be positive, and you can just manually check up to 1,000. So we have one recent paper with Mark on an application of this specifically for predicting the structure of biomembranes in cells. And we have a new paper that will come out very soon, hopefully, or some preprint will come out fairly soon, which gives an algorithm, really, a SAGE implementation, where you give a definite function, and aside from some technicalities, it will give a bound that'll say that it's positive from this point onwards, and then you just check before that. So stay tuned, and we should have something exactly answering the question you're interested in.
That's very interesting. Thank you.
Okay, thank you. Other questions? There are some questions in the chat by the organizer.
Any chance of getting...
read them?
I think there's...
Can you read them?
I can read them, yeah. But I'm having an echo from one of the organizers.
So there are two questions. So first question, could you comment a bit on the periodic constant appearing in your asymptotic results? For example, of the form A plus B times -1 to the n. I think this comes from these two singularities at 4 and -4.
Precisely, yeah.
Something special?
Yeah, so exactly. So just like in the univariate case, if you have 1 over 1 minus z squared, you'd have a singularity at z is equal to 1 and -1, and that's why you only have the even terms appearing. So again, we can have, when I stated my results, I said you have sort of only one minimal critical point, but you could have others with the same coordinate-wise modulus, and then because you have these two singularities, maybe one is negative the other, and so you get these kind of periodicities appearing there from having multiple singularities that contribute. So just like the univariate case.
Okay, thank you. There is a second question from the organizer. Imagine you have a discrete structure converging to a continuous structure, for example, random walks and Brownian motion. And somehow you are able to describe asymptotics of the random walks. Would you have some hope to pass to the limit and to have a way to prove the ACSV allows to have a commutative diagram? So the analytic combinatorics.
So I'm not
okay.
I'm not 100% sure I understand the question, but I will say that if you pass to the continuous object and you're able to get asymptotics using the very powerful techniques they have for that, it does tell you something about the singularity structure, or what singularities you would expect to contribute from the multivariate analytic combinatoric side, which you could then use to get asymptotics about the discrete structure instead of the limit. So you can use information from the limit to inform what you're doing with these multivariate generating functions, and then get more information on the discrete side in that sense. I'm not sure that I fully understood what the question was saying to answer it, but that's something.
Yeah, okay, it's fine. Thank you. Okay. I can give you some more details per email. Thank you very much.
Do you want to add something more, Kilian?
No, thank you. That's fine. Okay. Thank you, Michael.
So, there are questions from the audience here.
Yes. I think Andrew had a question. I can read it out, maybe. So Andrew. You can read it out. Go ahead.
Thanks. Yeah, so I wrote the questions in the chat, but maybe I can clarify.
Sure.
Yeah, please go ahead.
Yeah. So the first question was just, since you got constant terms for, I guess, just the definite cases of walks in the quarter plane, right? Is there any chance you could get constants for, more general cases?
So, the diagonal of a multivariate rational function will be definite. Of course, our theory actually works for meromorphic functions. So you can try and apply it and get definite things, but
sorry, I should turn this off.
Okay, thank you. Yeah, so theoretically you can get asymptotics for non-definite generating functions. To actually do this for the lattice path examples, I'm not so sure it will be possible. In particular, I believe there's work of Kilian, Aline, and Bruno, I hope I got everyone, that shows that you have n to the alpha, and alpha is an irrational number, and trying to recover that, I think using these methods would be it's not going to happen. So in general, we can handle non-definite things, but for these lattice walks, I don't think it's going to be possible to use that approach.
Okay. And so another question is, I guess your ratios of rational functions end up being equivalent to multivariate recurrences with constant coefficients or something. So is there any chance that you could do something where you have some linear terms in recurrences, I guess? Like if you know about the work I did with Michael Wallner and Wenji, it sort of ends up being, you end up having some linear terms in recurrences and then some funny stuff comes up. But
yeah, as you say, if you have a multivariate rational function, you'd get this multivariate recurrence. But of course, for work of Mireille and Marco Petraszek, maybe, we know that if you have a multivariate linear recurrence, you can get very horrible generating functions. It doesn't have to be rational anymore. So so it would be possible, but I mean, there are going to be examples with multivariate linear recurrences that we can't handle just because you have really horrible generating functions, like the examples in their paper.
okay, thanks. I was just suggesting tricky, places for potential expansion or something.
Yeah, no, thank you. Yes.
Thank you.
Okay, so are there some further questions? Okay, there is another one.
May I try one?
Hello. Is Andrea asking a question?
As you want. I don't know who you are, by the way.
Yeah,
Okay.
I think,
Okay, then, okay, so go first, Andrea. Go ahead.
Okay. I might not have understood something, but you were talking at the beginning of this algorithm very well implemented by Mark Mezzaroba for calculating this connection constant, or I don't remember the name, which is the change of basis when you have the expansion near one point and another point. But those are only numerics, and when you find those numbers, even if they look like integers or pi divided by a rational or something like that, you don't know how to certify that.
Mm-hmm.
Is your method also giving an alternate way of certifying those constants, or it's just something completely different that calculates what you need without using that method anymore?
So, I mean, we get these integers, and in some cases we know what the integers are. So if you have minimal points, these minimal singularities, we know that the integers will basically be 1 or 0, or maybe -1, depending how you orient things. If your set of singularities is the union of hyperplanes, we can again compute exactly what the integers will be. So it'll be ±1 or 0 again. But the problem is that if we have these non-minimal points, then we really have to kind of do these gradient flows or somehow understand something about the geometry, which could be quite difficult. And so one way to do this, the way we're doing it right now, is to use this technology, this code that Mark has developed, which, by the way, I put the link in the chat to the package. So it's on Manuel Cowers' GitHub page for anyone who's interested in it. So we're using this to find these constants, but there potentially would be other ways to try and figure out what these constants are. In fact, this example I showed where we get a 3, this was really the first natural example we had where it wasn't a 1, a -1, or a 0. So Robin Pimentel has a student right now who's trying to understand what this 3 is, so come up with another way of understanding why there's a 3 there instead of just this computational method. Because this is actually, the example I showed is part of a family, and so from that Doran studied. And we can do it for any fixed value, so there's a parameter, and for any fixed value of the parameter, we can compute the differential equation and figure out what the constants are. But of course, it gets more expensive as you increase the parameter, and we'd like to do it more generally. So understanding other ways of getting what these integers are is something that's very interesting, but I think could be very difficult because a lot of people have thought about these kind of topological questions before and haven't been able to really come up with anything.
Maybe a more precise version of my question.
Sure.
Say that you have functions which are the 2f1, the Gaussian hypergeometric, and you pretend that you don't know the transformation rules for this hypergeometric, which in fact exist and are really toy model in a sense because they're very ancient of those connections.
I don't know what the transformation rules are, so it's easy for me to pretend.
Okay. I skipped the question then because it would be too long.
Okay, there is another question in the audience, please.
Yes. So, hi, Steve. This is Ling Xiao. So first, I would like to clarify my understanding about the picture of for more theory that you are using. So I'm not sure that I understood the pictures correctly. So, for example, on the page 54 of your slide.
Sorry, I'm no longer the boss. I can't go backwards. It's been taken from me. I'm very sorry.
Okay, so but you see what I'm talking about, right?
I understand. Yeah, I know the question. I know the picture you're asking.
Yeah. So what?
Do you want to ask more?
Yeah. So you have this surface, and on which you draw a curve, and you try to push it down.
Yes.
So the surface it represents the singular variety of your function, right? And so the curve, if I understand correctly, the curve doesn't really live on the surface. It actually lives on the complement of the surface. The surface is kind of an obstacle that blocks it.
So there's two ways to think about it. If you see Robin Pimentel, he was kind of waving his head back and forth. He was thinking the exact same thing. So one way you can think about it is that you deform thank you, sir. That's a very nice rendition. So one way to think about it is you deform your domain of integration to be arbitrarily close to the surface. Now, if you know how to flow on the surface, you know how to flow on the complement because you just flow, epsilon off the surface and you go like that. Now, the other thing you could do is you could actually use these residue computations, these multivariate Leray residues, to essentially take your d-dimensional domain of integration and say take a residue and then end up with a new integral that lives actually on the surface in a smaller number of variables, and then flow from here. So there's two ways to picture it. You could either picture that you're in the complement but epsilon close, or that you have done some computation previously to restrict to a new integral that lies on the surface of singularities.
Okay, I see. Thank you. That completely answers my question. And another maybe a question about a small detail is that at some point you said the exponential part of the asymptotics always depends smoothly on the parameter, like the temperature.
In that example.
In that example.
In this, so in the example, in the final example that I gave, where these threes appeared with the multiplicities, actually the exponential growth does not very smoothly in that case. So on this main diagonal, you would expect to get an 81 to the n, like sort of what you would expect from the basis of three things that I showed on the first slide for that example. But the 81 to the n actually drops out. So this can't happen really if you have smooth singularities. But in this case, your singularity, it's called a cone singularity. It looks like w squared minus x squared minus y squared minus z squared. So it looks kind of like two three-dimensional cones meeting at a point. So with these weird singularities, you can have sharp changes in the exponential growth.
Thank you.
So thanks. I think we have another talk. So we should go ahead with that. So thank you very much for your very nice talk, and clap hands again.
Thank you.